China has just rocked the global tech world. In a stunning announcement, Chinese scientists revealed a new way to make two-dimensional chips that could change everything. The chip war, long dominated by the West, may never be the same again. Suddenly, the balance of power is shifting east. The breakthrough centers on a material just a few atoms thick, two-dimensional semiconductors. These were once only seen in labs. Now China claims it can make them on a scale big enough for real-world chips. This isn't just incremental progress. It's the kind of leap that resets the race. Governments and chipmakers worldwide are taking notice. The news is racing through boardrooms and intelligence agencies. Is this the moment when China truly closes the gap with the West in advanced chip technology? The story of this discovery is more than a headline. It's a tale of scientific grit, fierce competition, and the promise, and peril, of a new technological era. For years, scientists and engineers have dreamed of harnessing the power of two-dimensional materials to create better, faster, and more efficient computer chips. The promise of these materials has captivated the imagination of researchers worldwide, fueling a race to revolutionize the electronics industry. These remarkable materials, which are only a single layer of atoms thick, have the potential to dramatically shrink the size of electronic devices while simultaneously boosting their processing power and energy efficiency. Imagine computers, smartphones, and sensors that are not only smaller and lighter, but also far more powerful than anything we have today. But there was a major catch: making enough of these two-dimensional materials, and at a high enough quality for real-world use, proved to be nearly impossible for a long time. The challenge wasn't just scientific curiosity, it was a fundamental roadblock for the entire industry. The dream of 2D chips stayed just out of reach. The main problem was scale. In the controlled environment of a laboratory, it's possible to make a tiny flake of perfect material, just a few microns across. But that's not enough for practical applications. The real challenge is to grow large wafers, thin, flat disks that are big enough to be used in manufacturing real chips. Most attempts to scale up ended in disappointment, producing only small, patchy, or flawed sheets that couldn't be used in commercial devices. Defects were everywhere, ruining the unique properties that make 2D materials so promising. Quality was just as tough to achieve as quantity. Even when researchers managed to make larger samples, unwanted impurities and imperfections would creep in, undermining the material's performance. These tiny flaws might seem insignificant, but in the high-stakes world of semiconductors, even the smallest imperfection can cause catastrophic failures. A single defect can kill the performance of an entire chip, rendering it useless for advanced electronics. This bottleneck, scalability, and purity became known as the wafer problem. It held back the entire field, frustrating scientists and industry leaders alike. Without a breakthrough to solve this issue, two-dimensional chips would remain nothing more than a fascinating lab curiosity, never realizing their potential as the future of technology. When it comes to creating two-dimensional materials, those atomically thin sheets that are revolutionizing electronics, researchers have relied on two main techniques. The first is chemical vapor deposition, or CVD, a method that has become a staple in advanced materials science labs around the world. The second is metal organic chemical vapor deposition, better known as MOCVD. Both of these methods have been instrumental in pushing the boundaries of what's possible in chip manufacturing and nanotechnology. At their core, these techniques work by growing a thin film of atoms on a surface, building up the material layer by layer with incredible precision. This atomic-level control is what makes them so valuable for producing the ultra-thin materials needed in next-generation electronics. In fact, they are considered the workhorses of modern chipmaking. CVD, for example, is elegant in its simplicity, at least in theory. The process involves heating up gases that contain the atoms you want to deposit. As these gases flow over a surface, the atoms settle down and bond together, gradually forming a thin, uniform sheet. It's a bit like painting with atoms, one layer at a time. MOCVD operates on a similar principle, but it uses metal-based chemicals as the source materials. This allows for even greater control over the composition and properties of the resulting films, making it especially useful for complex semiconductor structures. Thanks to these methods, scientists have achieved remarkable progress in fabricating thin films and advancing semiconductor technology. The ability to inspect and manipulate materials at the atomic scale has opened up new frontiers in electronics and materials science. But despite these successes, both CVD and MOCVD have run into serious limitations when it comes to making truly two-dimensional materials. The growth process is excruciatingly slow, sometimes taking several days just to produce a tiny patch of material, barely large enough for research, let alone industrial use. Even worse, the process is prone to contamination. Unwanted atoms, like oxygen or carbon, can sneak into the mix, disrupting the delicate atomic structure and compromising the quality of the final product. This contamination can ruin the electrical properties that make 2D materials so special. The combination of slow production speeds and the risk of dirty, defective output simply isn't acceptable for large-scale manufacturing. The semiconductor industry demands large, pristine wafers, produced quickly and reliably. With these old methods falling short, the dream of a two-dimensional chip revolution seemed out of reach. It became clear that if the world wanted to unlock the full potential of 2D materials, a radically new approach was needed, one that could deliver speed, scale, and purity all at once. Without such innovation, progress would grind to a halt, and the promise of next-generation electronics would remain just out of reach. Enter Oxy-MOCVD, the star of China's recent breakthrough. This new method takes the old MOCVD process and adds a clever twist: extra oxygen. The result is dramatic. Suddenly, two-dimensional material can be grown not just faster, but cleaner and larger than ever before. The secret lies in how the oxygen is used. In traditional MOCVD, too little oxygen leaves impurities. Too much can damage the crystal. But with precise control, Chinese researchers found the sweet spot. They blasted the growth process with just the right dose of oxygen, allowing atoms to arrange themselves perfectly. The results speak for themselves. Using Oxy-MOCVD, teams grew two-dimensional semiconductor wafers up to 8 inches across. Industrial scale. Even more impressive, the films were nearly flawless, with record-low contamination. This wasn't just a tweak, it was a whole new playbook. Where others had crawled, Oxy-MOCVD sprinted. The wafer problem, once a wall, now looked more like a speed bump. The numbers are staggering. Oxy-MOCVD grows two-dimensional wafers about 100 times faster than old methods. What used to take a week now takes, well, less than 2 hours. For chipmakers, this is a game changer. Speed means lower costs, less energy, and more chips on the market. But, speed is only half the story. The process also delivers unmatched purity. In earlier methods, stray atoms would sneak in and wreck performance. Oxy-MOCVD's controlled oxygen flow keeps those invaders out. The result is crystal clear, defect-free material ready for high-end chips. This combination, fast and clean, finally makes it possible to manufacture two-dimensional chips at the scale industry needs. It's like moving from hand-carving wood to precision laser cutting. Suddenly, the impossible becomes routine. No wonder experts are calling this the missing link for two-dimensional electronics. For the first time, the dream of mass-produced, two-dimensional chips looks real. Oxy-MOCVD wasn't the only breakthrough. At the same time, other Chinese teams tackled a related challenge: how to spot and fix defects as wafers grow. Their answer? Real-time monitoring with advanced imaging and feedback systems. Imagine watching a city being built, brick by brick, while it happens. That's what these researchers achieved for atom-thin materials. By using special microscopes and sensors, they could observe the growth process second by second. If defects started to appear, they adjusted conditions instantly. This level of control slashes the defect rate even further. Clean wafers come off the line, ready for use in the world's most demanding chips. With fewer flaws, yields go up and costs fall. A huge win for manufacturers. Together, Oxy-MOCVD and real-time monitoring form a 1-2 punch. Grow wafers fast and clean, then catch any slip-ups as they happen. It's a recipe for world-class production. None of these advances happened in isolation. China's leap forward was the result of tight teamwork among its top universities and research labs. Names like Tsinghua University, Fudan University, and the University of Science and Technology of China, or USTC, appeared again and again in research papers. Different teams focused on different pieces of the puzzle. Some pushed the boundaries of wafer size, others zeroed in on purity, or on the real-time observation techniques. They shared results, swapped samples, and even combined their processes in joint experiments. The pace was, honestly, breathtaking. In just a few years, Chinese teams jumped from millimeter-sized flakes to full-scale 8-inch wafers, each breakthrough built on the last, creating a snowball effect of progress. This collaborative spirit is now seen as a model for innovation. By pooling brainpower and resources, China's research ecosystem outpaced global rivals, setting a new standard for scientific teamwork. These technical leaps are shaking the foundations of the chip industry. China, long seen as a laggard in advanced chips, now has a powerful new tool. If two-dimensional chips take off, supply chains and market leaders could change overnight. For years, the United States and its allies used export controls to slow China's chip ambitions. But breakthroughs like Oxy-MOCVD are homegrown. They can't be sanctioned or blocked. Suddenly, China has a path to leapfrog old obstacles and define the next wave of chip technology. This matters for everything from smartphones to artificial intelligence to military tech. Whoever leads in chips holds the keys to the digital world. Even small shifts in technology can tip the balance of economic and political power. The chip war is now a race on new turf. The stakes are higher than ever. The question is no longer if China can catch up, but whether it might soon take the lead. Is this the turning point? Are we standing at the edge of a technological revolution, or simply witnessing another milestone in a long journey of innovation? China's two-dimensional chip breakthrough could signal the dawn of a new era, one where the boundaries of what's possible in computing are redrawn. These chips, thinner than a strand of hair, promise to pack more power into smaller spaces, potentially reshaping everything from smartphones to supercomputers. Or, it might be one big step on a longer winding road. Scientific progress rarely moves in straight lines. Each breakthrough is built on years of research, trial and error, and the path ahead is filled with both promise and uncertainty. The world is watching closely to see if these lab successes can truly translate to mass production and real-world products. Scaling up from prototypes to billions of chips is a challenge that has tripped up even the biggest players before. If they do succeed, the impacts will ripple far beyond the tech industry. Economies could be reshaped, industries disrupted, and new opportunities created for those ready to adapt. Artificial intelligence, quantum computing, advanced military systems, and even healthcare could all be transformed by this leap in chip technology. The potential applications are as vast as our imagination. Supply chains might shift, national strategies could change, and the balance of power might tilt in new directions. But big questions remain. Can the West respond quickly enough to keep pace with China's momentum? Will alliances strengthen or fracture under the pressure of this new competition? Will China's new two-dimensional chips truly dominate the global market, or will new barriers, technological, political, or economic, appear to slow their advance? The race is far from over. The only certainty is that the chip war has entered a new phase, one defined by speed, relentless innovation, and a global race for the future. Every nation, every company, and every researcher is now a player in this high-stakes contest. As you watch this story unfold, ask yourself, are we witnessing a true revolution, or just another round in a never-ending contest for technological supremacy? The answer may shape the world for generations to come. The next chapter in the chip war is being written right now, and its outcome will echo across industries, borders, and the very fabric of our digital lives.